also the talk of tonight is going to be around this book, so we'll cover it later. We are ambassadors of the Chatbot Summit, so you can get 20% discount. And if you also want to be a speaker, then this, we can connect you to the organizers. And same thing is for rework in Amsterdam. We got a special discount for the community in the Machine Intelligence Summit. And also, you can speak. I don't know if they have still spots left, but they should be. The fourth promotion is about DataCamp. So DataCamp provides training, online courses, mainly on Python and R, on the data science Python and R. And we also arrange a special prize for the members. That's it. So we are on any social channel, all of the popular social channels. So feel free to take picture and mention us and share. So we want to keep the media involvement going on. That's it. And now I'll ask for our host and sponsor of this event, which is Think Big. So let's thank
Thank you. Greetings. We're glad to be here. My name is Max Goff. I'm a principal with the Think Big Academy. I've been here with my colleague, Dr. Rob Snowden Lambert. He's a multi-volunteer man about town. So you know, he's a science fiction fan and part-time hacker. Was it hacker?
Not a part-time hacker. Full-time hacker.
Full-time hacker. So we're with Think Big Analytics, and we're very pleased to be helping sponsor this meetup here in Think Big Analytics. We don't want to take too much time to talk about us. We want to give as much time as we can to our key speaker here, Laura. But a little bit about Think Big is a big data only service provider. We were the first to be the only big data service provider on the planet. The very first to offer the technology agnostic approach to focusing on solutions that are based on client data. That's really what our focus was. We're not management consultants. We're not financial consultants. We're data consultants. That's what we do. We were started in 2010. We were acquired by Teradata in 2014. It was a strategic partnership, a strategic buyout that occurred. And since then, the reason Think Big founders were motivated to take the deal was to get the investment capital in order to grow. And that growth since the acquisition has been phenomenal. We have gone from, we crossed that here 300. The last time this slide was presented, we were 300. We're now at 1,000. That's how fast we're growing. We base everything around an architecture that we call velocity, the velocity framework, that includes several different buckets of offerings, architecture roadmap. So we go in and do an analysis and figure out how a client can use their data, which we had a prize-winning product that was just announced earlier this year. It's not a product, it's open source. It's called Kylo. Maybe you've heard of it. It's Project Accelerator, something to allow for creation of huge multi-petabyte data lakes in a relatively short time. We've also got great data services, analytics ops. We also have training, the Academy does, and our managed services as well. Think big, start smart, scale fast. That really summarizes very succinctly what it is we do. Think big. Don't think about just a use case or saving a few dollars using big data technology. Think about a sustainable competitive advantage based on your data. That's the audacious approach we take with our clients. A sustainable competitive advantage. Because it's based on client data, that's a promise we can help them realize. Technology may change, Moore's law may continue, but what won't change is that ownership of data. As long as a client has data and they can leverage their data to find the value that's latent, hidden in that data, they can create a sustainable competitive advantage. Start smart. what we do, based on having done hundreds of client engagements with big companies, we figured out those best practices and patterns that allow us to replicate some of those best practices with new engagements. We have project accelerators like Toddler. We have others coming for data science that help us get started faster so that companies can scale fast. So that's more than just a tagline. It's actually how we do business. Think big, start smart, scale fast. And then I have a pyramid, because we have to have pyramids. And Rob, what is this about? What is the pyramid?
Thank you, Max. Hello, everyone. So I also like to do a bit of karaoke, so I'm very happy with the microphone in my face. That's really good. So the question about us from what we're seeing that is really, where do we operate? Do we do like small scale things? Do we do engineering only? Do we do data science only? Something like that? Well, actually, we do everything. It's think big. We think big, right? We do implementations of Hadoop ecosystems, data lakes, petabytes of data, that kind of scale. Right? We'll build the thing for people. We'll then run operations on top of that, or manage services, or whatever, or we'll do consultancy on top of that. We'll help people build a great data lake. We'll help them operationalize analytics. So that's really pretty cool. That's where I specialize in, actually making that analytics, those models run in production, real time, high data volumes, things like that. We call analytics ops. And then really the tip of that pyramid, what we are really excelling in right now is that deep learning sort of area, artificial intelligence. You know, people have lots of words for this sort of area, and we'll hear a lot more from Laura about that in just a minute. But well, what are we doing there? Well, you'll hear about self-driving cars. We're doing deep learning for fraud detection. We're doing mostly it's TensorFlow, right? It's open source. It's really cool on massive data sets. Hundreds of thousands of transactions.
So Rob, other than eating pizza and listening to an awesome talk, what do we want people to do?
Well, we really kind of like you to join us. so we're hiring, but also if you have any projects you'd like to do with us, that's fantastic. Please do come and talk to us, see what project you're doing, and let us help you and help us do projects. But we're hiring all types of people. We have a big vision. We think big about how to do data science.
Yes, we do.
So we need all types of people. We're building a diverse global team of international people flying all around doing the best projects in the world. Right? Doing self-driving cars in Japan, doing self-driving cars in the Netherlands, doing fraud detection all around Europe, etc. So what we need is people with diverse backgrounds. So we need data scientists, that's for sure. If you're all data scientists here, that's great. We also need data engineers, business experts. We need BI professionals. We need data architects. We need we need all kinds of everything. We need thought leaders. We need open source evangelists. We need project leaders. We need project managers. We need absolutely everything. So if you know somebody and they're good, please send them our way.
Right here. Analytics.com, big-data-careers. Just go over there, have a look around, and if you're interested, we'd love to hear from you.
And so you can remember our name. We've got some nice goodies for you to take away with you tonight. So please do take the stuff. It's free. Right. I also want to introduce our next speaker. So Laura. Oh yes.
I think before we move to the next speaker, I just realized maybe we need to do a little bit of fix of the setup. Because I've seen the lights that are very on the recording. You can't see the text.
Okay.
Yeah. Would you like to turn on the light on the screen?
That would be fine. Yeah, sure. We'll do that. No worries.
That would help.
Yeah, and also I don't know if I'm asking for the people on the back. If you want to move closer, then we have plenty of space. We're gonna get close to the screen. It's up to you. I wasn't on that line, and I couldn't really read, so I'm guessing that people on the back can hear.
It's very bright now. I think everybody up. Are we all right?
Get as close as possible.
Okay. Does this help?
It's all white. So I think you mean so.
Yeah, it works.
Yeah, that's all that. Sorry for that.
How's everybody doing? I heard some people came all the way from Bologna. So it's pretty far. It's pretty much another planet.
We need to kill these lights over here.
No, that's
There.
Fabio.
There's a bit of delay.
Yeah, that's
Yeah,
better.
that's
Better.
You just need to get tighter, I think.
yeah.
I think it's.
We good? So I should introduce Laura. We've known Laura for several awesome months. And I think the most interesting thing about Laura was she speaks Japanese. She has a PhD in applying machine learning to human brains. Pretty awesome. Now she studies a different type of brain, artificial intelligence, deep learning, applying deep learning to create self-driving cars with us at Think Big. So go ahead, Laura.
Thank you, Ra. Hello, everybody. So, like Rob said, my name is Laura. I do not speak Japanese. Apparently, common misconception. I'm trying to learn. That's true. Do not speak. I will try to give you a bit of an overview of artificial intelligence in companies. Where did it come from? Where are we? Some applications, and where do we see this going? So, but first of all, so companies have, of course, not just started to use data, but it started somewhere else. It started just trying to describe what's happening now with descriptive statistics, and then moving on to more predictive. So now we know what's going on now. We say something about what will happen in the future, so that we might be able to. Then along came the internet. Real-time models started to be more interesting, high-frequency trading, how much I bid to put an ad on this website that the person was just about to visit, so a millisecond time scale. So that was sort of moving from these descriptive statistics to having models that could run continuously on systems. And then after that, people realized it would also be nice to have these models update themselves as new data came in. So this was sort of the next step in using data in companies. So being able to deploy a system that has a model that can update when new data comes in. And then after that, is sort of where we see the current statuses with the next step, artificial intelligence. So of course we've been here for some years now. It's not like entirely new, but a lot is happening in this field. So why now? Why all this hype about artificial intelligence and deep learning now? Because it's not a new research field. It's been around since the 1940s actually. It started in the 1940s, and then a lot of people got very interested in it. A lot of work was done. And then people got disappointed, and no one really worked with it. And then interest sort of came back, and people worked with it for a while, and interest declined. And now, in 2006, interest really picked up again. And in 2012 was also sort of a milestone with some really important advantages within the field. So that it's now really. It's now really an active field of research and application again. And there are several reasons for this. There's hardware. Before, in the 1940s, the hardware was only good enough to have very few neurons in a neural network. And with only few neurons, you can't really learn a lot. You have to have a lot of neurons to be able to try to model the world correctly. So that's one of the reasons that it's really picking up again now. We have better hardware. Also, we have more data. Data is really important for neural networks. With the internet, everything's being recorded. This is being recorded. Always everything's recorded. We have a lot of data to train the neural networks on. And with the hardware and the data, research got more interesting and companies got more interested and started investing. Google, Microsoft, Facebook. So there are all these factors coming together now to drive a virtuous cycle. And this is just a graph to sort of prove the point. So this, the y-axis shows the number of mentions of artificial intelligence in reports from companies, and the x-axis shows time. And this really looks like exponential growth, right? It's really amazing. So there was a quote from Gartner earlier this year that they predict by 2020, 30% of the CIOs in company will see AI as a top 5 priority. And once again, so there's this lady called Sivan Silis who got interested in this field a few years ago, and she went out and did a survey of the companies that use deep learning. So we see the chart that she made in 2014, the end of 2014 up there, with all the companies that use deep learning. And then she did the same exercise a year later. And again, last year, 2016, she did the same survey. And it's really, again, impressive to see how many more companies are using AI now. Just in 2 years, how many companies are actively using AI to drive their business and offer value to customers. So deep learning, how is it different? Well, there are several things. It requires much less domain knowledge to get valuable information out of data. Many more traditional approaches would require more manual feature engineering, so you would have to have an idea of what are the important things in data, how do I make the most informative features so that the model has reasonable inputs to start with. Networks, the deep learning with several neural networks stacked on top of each other do this automatically, so that eliminates the manual feature engineering. So yeah, so that's basically actually the main differentiator, that they can deep learning neural network can learn all of these features. Intervention. And again, we see the improvement. So this is from a contest that runs every year, and we see the errors. The y-axis, we get the time. On the x-axis, the errors are just decreasing year by year by year. So this is the performance of the winning entry in this competition. Now moving on to some applications. So first, I've just sort of recently really become convinced that deep learning really is a very big and very quickly growing field. So I used to be more, I've always thought it's a good tool, but I might have been more reserved about how useful a tool it actually is. So I just wanted to talk a bit about some of the limitations. So of course, if you want to say anything about causality, this is not the way to go. A lot of other methods have the same problem, of course. So if you want to say anything about causality, deep learning might, at least you'd have to tweak it a bit. Then it needs data. So if you don't have a lot of data, you're probably better with a smaller model with more assumptions, a more rigid model that is not as. And then also, if you have to have updates to the model quite frequently, deep learning might not be the way to go with it, because it does take a long time to train the model. It also takes longer time to make predictions with deep learning models compared to very simple models like linear regression, but not nearly as long as it takes to train them. So those would be cases where you wouldn't use deep learning. On the other hand, there are many cases where deep learning would be a very good bet. If you have a lot of data, which, as I mentioned, we have quite more often now, if you have a lot of data, deep learning might be able to help you find complex patterns in that amount of data. if you suspect a lot of non-linear interactions in the data and very complex patterns, deep learning could be a way to go. Recently, last year or year before last, Google used deep learning to make a model of their server centers, their data centers. So they have a lot of recordings going many years back of their sensor measurements, the temperatures, the speed of the fans that cool the servers, a lot of sensor measurements. And their data centers use a lot of energy. So they trained a deep learning model to predict if these sensor measurements are like this now, how much energy am I using, and how will the data centers overall state be in the next few hours. They trained this deep learning model, they gave it to the operators, so the operators in the data centers can now try to tune various parameters, and then they'll get a prediction of what that will do to the data center in the future. And using this model, the operators were able to optimize the energy usage, so their total power consumption fell by 15%. So this is quite impressive. There are also some caveats of deep learning. There are caveats of all models. I think one of the reasons that you have to be more aware of it with deep learning is because deep learning can really work so well. It can learn the training data set really well and learn the distribution of the data. But that also means that if you have data with biases in it, if you have a human language, you have a lot of biases. It turns out that a model was trained to learn sort of what compares to another thing in language. And one of the things it learned was that father is to doctor as mother is to nurse. So essentially it has learned that males tend to be doctors and females tend to be nurses. And this is probably a true bias in our language, but it's not one that we want our models to learn. Imagine this model were then used to place job ads. Males would tend to be shown ads for doctors, and females would be shown ads for nurses. And that might not be something that we're interested in. So you really have to consider your training data when you train a model. You will teach the model what the training data contains. So yeah, that's one thing. Then there's another interesting thing. These pictures. So here's a column of pictures that are classified correctly by neural networks, by deep learning models. Then there's this column of noise, and when you add this noise to this column, you get these images, and as humans we can't tell any difference. But if you feed those images on the other side, and in the last column to a neural network, it will misclassify them. It'll get very, very wrong classifications. I don't remember the classifications. And other models may have the same problems. In mind, it's not magical. You still have to keep your human reasoning about this. So now going up to some of the awesome stuff that it does do very well. So this is just a survey from the deep learning 4J framework authors, where they looked at which sectors used for which use cases. So basically we just see that it's used for a lot of stuff like sound sensors, text, image, video. It's used for automotive settings, for credit card fraud detection. And so here's one of the use cases, which is mobile personalization. So if you, so Google of course has Play Store, and once in a while when you use Play Store, you may know the app that you want on your phone, and you will just type in that link. But oftentimes people don't know the exact app they want, they just know sort of what sort of function they're looking for this. So they search in they put in a text query. And Google had apparently a lot of difficulty finding out how to find the right apps to help solve this problem that the user was trying to solve. For example, they, at some point there's a game called Plants vs. Zombies that's not educational at all, but that was classified as educational by one of the older models from Google. So they ended up putting some research effort into this and coming up with this architecture, which is a deep learning model up here that takes care of the generalization. And then there are some odd cases like the pants versus zombies. There are some weird interactions that do not fit into the generalization behavior that's in most of the training data. So you have a linear regression model with the interactions at the bottom. So that's actually sort of an interesting way to combine these things. And then there's anti-fraud. So banks are in charge of transactions, and with all the developing technology, more mobile apps, more mobile payment solutions are also coming onto the market, and these are used more and more frequently to pay brands, to pay stores. This also makes it more. This also makes it easier for criminals to make more of these transactions. And with every fraudulent transaction, of course, the bank loses money, but if it's too strict and flags too many of the transactions as fraudulent, it will annoy customers. So this is an important business use case for banks. You really want to only flag the transactions that are fraudulent and those you really want to catch, so you don't lose a lot of money. So instead of using the traditional approach, which was based on handwritten rules that people had figured out, we tried to work with the bank to use a more data-driven approach, and several models were tried out in this. So random forests were used, and recurrent neural networks were used in various technologies. And the project was run as a first simulated results, and the challenger testing, and the fact that finally the system was actually put into production. And as far as I've heard, it's actually doing well, better than the traditional handwritten rules. Then with this, so this is what everyone is talking about in the media. You often see this. So self-driving cars, will they be out next year? When will they be out? They probably won't be out next year, but a lot of car companies are looking to deep learning to improve various aspects of driving. So there are several use cases in driving. You can put a lot of sensors on cars. You can put cameras and other things. And some of these things that deep learning can help with, if you have cameras, is when a car drives by, for example, or congestion, a lot of heavy traffic, the car might be able to recognize this automatically and tell a central server that, hey, look out for this area. Something's going on here. And then the central server could tell all the other cars with the same software, look out here. Maybe you want to try to find another route to avoid this heavy traffic. That deep learning could be used for cars is improving the environment within the car, making the temperature better suited to the person driving the car, such things. Oh yeah, and of course parking assistance, which we're already seeing in Tesla, but I'm actually not sure what Tesla uses. I was sort of trying to Google around, and people are talking about Tesla's cars claiming to need some training, so it seems that they may use at least some machine learning approach, but I'm actually not quite sure if they use deep learning or not. But it would be a very obvious case. Automated check processing. So people still use checks. I'm not sure I've ever used one, but some people use those, and apparently there are a lot of fixed costs associated with this. And as the volume of checks being processed decreases, the fixed costs will take up a larger fraction of the total cost for processing checks. So this is another use case where deep learning can drive costs down, because a lot of the things involved in check processing are obvious use cases for deep learning, like recognizing handwriting, recognizing natural language processing. These are some of the problems that deep learning is often cited as being a good solution for. We'll move on to some conclusions and some content about how we do deep learning at Think Big. So there are still some challenges in deep learning. It's research-driven. Not a lot of deep learning methods are productionized in companies yet. Are actually popping up that offer deep learning solutions, but these solutions are packages, so they're probably very suitable for small to medium-sized companies that can afford these sort of standard solutions. But if you're a big company, you'll probably want a tailored solution that with deep learning to solve a problem that fits your needs exactly. And this is not very common yet. A lot of companies do not yet have tailored deep learning solutions. And I'm not sure, I think more and more companies are probably starting to do this, but it's not very common yet. And limited access to talent, of course, so these would probably be some of the people in this room. But there are not a lot of people who have a lot of hands-on experience with deep learning yet. As I said, it's pretty recent. It's only in 2012 that it really started to pick up for image recognition. So that's all by now 4 or 5 years ago, but still time to get into the field, really get to know it, really use it in projects. It takes a long time to really get to know the field probably. And so one thing is research and knowing it really well theoretically. Another thing is deploying it on systems where it has to run well. It has to be up to production standards. So the way that we do it at Think Big is we look at it in these phases. And it's usually a 6 to 12 month project to move through all of these phases. So there's a first a validation phase where you want to look at what's out there, what exists, what can we utilize, and is this a viable approach? Then you want to look more into how exactly would we use this, the architecture. You would get more detail into the specific use case. And you will also look at how much business value do you actually think this approach can gain for the business. Then there's the third phase, which is putting some of this into live testing, looking at how is it actually performing, and then finally the fourth phase of putting a system into production. Now, another challenge in deploying deep learning solutions in production settings is that you need analytics ops, which just refers to putting analytics into production. And to do this, you need cross-functional teams. The business support of the company, the people making the business decisions need to see the value of deep learning, need to be able to see where can these solutions help the company. You need data engineers, you need software programmers to actually do the programming. You need users of the software and of the solutions to tell you how do they want the software to work. You of course need data scientists to help with building the model, training it, and testing it, and so on. And you probably also need domain expert humans to say whether the results from the model are reasonable or not. So I think so since there are so few people with hands-on experience, we think of it this sort of onion structure, I guess you could call it. So in the middle we have dozens of experts who really focus on this area and make sure to stay up to date. They follow the research, they really know what's going on in the field. Then outside of that central circle, we have more than 200 practitioners who put deep learning into practice, but they don't also have time to really stay up to date with all the research. So they utilize the experts who are staying up to date. And then on the outer certainly we have a lot more people who have an idea of what deep learning can do, can help identify places where businesses might be able to derive value from deep learning and help to make this connection between deep learning and where businesses may derive value. So this is a sort of a summary of where we see deep learning, where was it, where are we, and where are we going. So, as I mentioned before, we started with some research results in the start of this decade. Then the digital giants, Microsoft, Facebook, Google, started to invest more heavily in this, started to utilize deep learning more. Now we are at the stage where more companies are starting to use AI, more companies are becoming interested, looking at opportunities. We expect more companies to start using deep learning to drive business decisions in a couple of years. And then a bit more into the future, from the 2020s, maybe we expect deep learning to be more present in society as a whole. So Amazon already has a store that they're beta testing in I don't remember where, somewhere in the US for their employees. So it's a store like a regular supermarket, but without any employees. So when you go into the store, you have this app on your smartphone that you scan, and then you go into the supermarket, you take things off the shelves, you put them back, like you usually do in the store, and various deep learning models, video cameras keep track of what's in your cart and what's put back. So when you're done shopping, you just leave the store. And that's it, you don't wait in a line or anything, and then they will send you a bill to your Amazon account. So to conclude, we see AI still moving forward. It's moving beyond labs into production. And I will just summarize without this, it's just points. And we really feel that you need a strategy and a roadmap to utilize AI to its fullest potential, know where you're going from the very beginning. You might as well start now, pilot now, and build capabilities that you can keep building on moving forward. So that's it. Thank you.
Questions for Laura, the chats from the audience?
Don't be shy.
Would you like to say a little more about hardware? You mentioned hardware being one of the key in the recent, the relatively recent resurgence.
Yeah.
You want to comment a little more about that?
GPUs have helped to drive that development. So GPUs are affected with them, so they need to process a lot of the same matrix calculations in parallel, which is sort of the same requirement that neural networks have. They don't need access to a lot of cache memory, which is a typical requirement of CPUs. GPUs don't have that, so they're more geared towards the parallel processing, which is also what neural network training is usually dependent on.
Do you see in the adoption of artificial intelligence as a solution, do you see that there's going to be a race in hardware with respect to the processing units, whether it be GPU or TPU or FPGA? Do you see a race there?
Well, we're already seeing that, I'd say. That there are a lot of use, quite often, of Google coming out with their new processors, and all of the big companies who are in this business keep driving bigger, better, faster GPUs.
Yeah.
So I'd say that we're already seeing that.
Yeah, cool.
So we've seen a lot of techniques example, in the machine learning environment, speaking about generative adversarial learning networks and things like transfer learning, so slightly different domains that might be related to deep learning, but are not really deep learning. So what do you think is like really maximum TP in this fourth generation of neural networks, or there is still a long future for that, or it's just the beginning for the companies because they need more time, so the implementation of these deep learning technologies that just start in the companies. What do you think about that?
I think it's still emerging. I don't think we're at the peak at all. So GANs are deep learning, right? Neural networks that sort of try to compete. So yeah, I'd say that companies seem to just be starting to adopt, to drive their business, to help business decisions, to solve problems that they can solve. So yeah, I see it as still an emerging field, especially for companies, not so much for research, still very active, but it has a long history.
Any other questions?
How hard is to explain these deep learning technologies to people that don't know anything about machine learning and just see a dashboard where things pops up, and you have to explain them how the machine actually decided that that thing had to pop up in front of them.
Well, it depends on the level that you want to explain it at, I guess. So if you ask a human being for a recommendation, like, you're local here, I'm visiting, what are the good restaurants? Then the person will tell me some restaurants. And I'm not going to ask you, how did you come up with those things? If you view the neural networks, the deep learning models in the same manner, then that's an easy explanation, right? It's just a model that's figured out the optimum answer, and that's what it gives you. To try to explain it, like, well, I started by defining these neural networks. I built a convolutional layer, and then I built another one on top of that, and I wanted it to have so many units. And that's not really going to convey a lot of meaning to the person asking. So yeah, so if you want to explain it at that very detailed level, you probably won't get very far. But if you just want to explain it more conceptually, it's just a mathematical model that has seen real world data. And from that, it has figured out a very likely optimal solution for your question. And that's easier.
For example, if I open Google, I click, I do my search, and I find the best pages, and it's okay. I will keep on using Google, and everybody's happy. But when you try to deploy something in a company, you want to be sure that the business people understand what you're going to deploy, and that the product will make happen to people outside your clients. And sometimes it can be not that clear. So that's why I was asking.
Right. So interpreting, so basically saying that if you change the color of the dress, then that will make more people buy the dress, something like that. Like,
yeah.
Or is that? Well, so there is research being done into this area and getting a better idea of how to interpret neural networks, why they make the decisions they make. That's an active research area. Does that answer the question better?
No, it was more on the really on the day-by-day work. So I didn't want to ask anything about research or studies of the bias or anything about decisions. It was really about how to explain these complex things to people that don't know anything about machine learning. And sometimes you need to give them some measures that really convince them that are not really technical, and it's not every time so easy.
Yeah, that's very true. And I think the best way to convince business people like that model works is probably to show that it works, I guess, because explaining the math behind it is probably not going to convince them anymore that it's the right way to go. I would suppose.
So really informal results. That's it.
But maybe I can answer that with a bit of a project analogy. working on a project where that was exactly the problem. So the end users, a group of a team of people that has to look at everything that our recommendation engine puts up, and they have to go and call people. And when people are like, why are you calling me? They have to say an answer, right? And they have to give something that's interpretable for the human on the other end. So it's a really weird situation. So then what we had to do is, as Think Big, as that organisation in that project, is go through their whole call centre and talk to everybody and teach them about machine learning and what it was and why it's good, and try and convince them that if they had enough time, they would come up with the same answer. If they just had enough time, but they don't want to have to spend 3 or 4 years doing mathematical equations to work out who to call next. They want a computer to answer that for them. And once you've got that final level of understanding that it's a calculator, it's a machine, it's just doing it slightly quicker than you can do it, then you raise a minimum amount of maybe those questions that start to be a bit more focused on, okay, in that situation, what was it that caused that answer? And then you can say, well, there are these sorts of interesting parameters about your customer in that case, and here are the top ones that cause that answer. And that can be a kind of interesting way to go forward. But there's a big need to educate into those spaces, and as data scientists, we're most often also educators.
What are the biggest challenges you face when scaling production these kind of models?
Well, we're still at the research phase at the project that I'm actively involved in, actually. So I myself have not been in a deployed project. Actually, maybe Rob, maybe you might be better.
Yeah, so that's the biggest challenge. Is that the question? The biggest challenge is a human challenge. The biggest challenge is convincing security experts that it's okay to deploy deep learning. The biggest challenge is finding the right stakeholders in an organization to support that idea. That's definitely the biggest challenge. The technological side of this, well, if it's real time, it's still kind of a challenge, right? But if it's batch or something like this, that's a kind of solved simple problem. Also, in certain sectors with certain types of data, you can be very sensitive. And that kind of dealing with that sensitive information, personal information, financial information, that can be really tough to make that audit trail, to really follow the regulations can be a very big challenge. And you need a lot of domain expertise, lots of subject matter experts there to work together. And that's why we couple lots of people together from very diverse backgrounds. So it's a great reason to work with Teradata, a kind of a global organization of industry experts who can come in and help us with these types of arguments, these types of questions to get it into production. But it's a good question because it's what we're dealing with every day. It's what we have to do in our job. So it's a very good question.
Yeah.
How does it work in Teradata? Normally, there are people that specialize really well in a particular domain, and others stay more general, or programmers would rest like in a more general environment, while data scientists try to specialize, for example, in finance and healthcare and other domains.
Well, I'd say it depends a lot on each individual's interest, what you want. So if you're really interested in a specific domain and want to spend time on that, then it would make sense to let you get into your field of interest and dig into that and help spread that knowledge to everyone else. But if you're just more interested in a specific sector and working with medicine, then that is an option for a lot of sectors because we have a lot of clients in, so it is possible to at least aim to stick with sort of one sector. Or if you just want to go around trying to do different projects, that's another option. So it really depends on the individual, I'd say.
We have room for a lot of different types. So it's a big company, 10,000 employees around the world, and there are a lot of different divisions. We're in the Think Big Analytics division, that's about 1,000 or 10,000. But there are other divisions in Teradata. Mainly what we do is consulting around big data and analytics, data science.
I know about you, about Teradata.
Yeah. Teradata.
I never spoke with you, so I was wondering how it works inside.
Teradata is a really old
Never
company.
got around or especially one domain or.
No, it tries to offer, it's a big enough company to have to accommodate different kinds of people with different career interests. And in order to keep people interested, it's got to allow for people who are interested in depth or breadth, depending on what you want. If you want to know a lot about a lot of different things, it's a good place to land. If you want to know a lot about one thing, it's also a good place to land. It depends.
Because I'm a fresh graduate and I don't really know what I like.
Well, you came to the right meetup. You should go to that website that we put up there and have a look. This could very well be. We hire not a lot of folks right out of school. It's a good place to start. It's really a good place to start. It's a very old company. It's been around for a long time. The name Teradata came when a terabyte meant something. The first database over a terabyte. But that was a long time. It was back when in the dinosaur. But it's been around. So it is one that has lasted. But it's a changing with times. I think big analytics is part of that change process. What Laura is doing, what Rob does, what I do, part of helping to make Teradata relevant in an era of deep learning.
Even in our division, big division, we have 25 different solutions, domains, and partnerships that rotate every year. So if you want to change completely your focus every year, you can totally do that. Or if you want to be that same domain, partnership, whatever, for 10 years, you can do that. And I've not done the same thing in 2 days in a row since I joined the company. But there are other people who've been there for 20 years and really are experts in a specific database or that specific way of transferring data. It's really quite amazing. We encourage both things, and we like people who have kind of a T-shaped profile, people who know a little bit about everything and a lot about a certain topic or a few topics. So that's what we.
Do you like to learn? Do you like to have fun? Okay. Then it's a great place. If you like those two things, I think it would be happy. It's the place to be. Well, how about some pizza? I'm ready for pizza. You guys ready for pizza?
It's the second talk, actually.
There is. Oh, okay.
I'll tell you yes.
No, of course we do. You'll introduce yourself, right, good sir?
Yeah.
Yes, of course.
All right, let's do this.
So, all right. So the second talk is going to be a particular example of how you can use deep learning for building an anomaly detection system. Okay. So. Let's zoom it. Okay, that's better. So what we will cover in this talk is, first of all, we're gonna see what is an anomaly, and then we'll go through a list of popular techniques that are used in shallow machine learning, and we'll see how deep learning can actually make the difference in those techniques. And in particular, we'll see the deep Auto-Encoders. And at the end, I'm going to give you an overview of H2O, and I'll show you a proof of concept example using a pulse detection signal. So the content we're going to see today comes from this book, which has just been released this month. And in particular, the content comes from the chapter about unsupervised feature learning and anomaly detection. So why this use case? Why anomaly detection? That's generally speaking, if you speak with any company doing machine learning, then anomaly detection is always critical to the business. Um, and in order to do so, one of the key component of a smart anomaly detection is the feature representation. And that's why we will see in this talk how deep learning is actually very good fit for learning smart representation of your data. So first of all, let's recap. What's an outlier? What is an anomaly? Okay. So often you find confusion, and the two words seem to mean the same thing. But actually, an outlier, this is a nice definition which I found on the web. An outlier is a legitimate data point that's far away from the mean or median of a distribution. But it may be unusual, like, I don't know, 9.6 seconds in a 100-meter dash, but still is within the realm of the reality. So it's something possible, just something, okay, outstanding, let's say. Let's call it outstanding point. But an anomaly is something different. Anomaly is an illegitimate data point that has been generated from a different process that generated the rest of the data. So it's a totally different process that started generating those data points. And we can classify them into three major groups. So when we model, so we got our data set, and then we need to start modeling entities. So the simplest case is the point anomaly, like the black sheep here, where each row represents one entity. But sometimes that's not enough, and you want to represent some context. So in that case, let's suppose we're doing anomaly detection on sales of ice creams, and I find a spike of ice creams. Doesn't mean anything, nothing, unless I specify the context, which is if I sell a lot of ice creams in January, there's something wrong. And then the collective anomaly is more traditional, like fraud detection kind of anomaly. So you have a sequence of events, sequence of data points, and is the whole sequence of things that happen that is suspicious. So what do you do? Take your raw data, you model one of those categories, and then you end up with some feature vector. Then it goes through the modeling part. So the typical case is the supervised anomaly detection, which is nothing more than a classification problem. If you have labels, of course. So if you can label what is an anomaly or not, it's just a binary classification problem. But anomaly detection by definition means that are very rare. So in your training data set, you're going to find very few cases of positive examples of anomalies by definition. So the data skewness and the lack of counterexamples is your major problem when you try to train your model using a supervised approach. What can you do? You can do unsupervised, like clustering, but I don't know if you guys are familiar with, have you done clustering before, like k-means or similar algorithm. There's one little problem. If your data points are representing too high dimensional space, so in other words, if your feature vector is too big, let's say even 100 of features, then each point is equally spaced. So the distance between each point converges to be the same for each point, no matter what. That's there's a mathematical proof for that. So that means that when you try to cluster with a lot of features, all the points, you get just random clusters. They make no sense. So what can you do? You can do semi-supervised, which is a hybrid approach. It's even sometimes you find in the literature with the name of novelty detection. And what that means is that you need to have a training set which you define as normal, and then that's your definition of what is not an anomaly. And then whatever doesn't look like the training set is an anomaly. We'll see that. So with those, with this combination of data modeling and algorithm modeling, there are a bunch of real-world applications you find in almost any sector. If you work in manufacturing, you can use it for hardware faults. In law enforcement, you can use it for, to reveal criminal activities. Very typical is network systems, find intrusions or malware detection. Frauds, of course, is one of the most popular. But sometimes not just about finding the bad guy, but for example, if you're doing marketing or you work in business strategy of your company, then you might want to use an anomaly detection to spot very profitable customers. So customers that outstand from the rest of your other clients, and they could be very high profitable. Or in healthcare, it's generally used for medical diagnosis. But all of this was the major challenge here. I like this quote from Andrew Ng. He says that coming up with a feature is always difficult, time-consuming, and requires a lot of expert knowledge. So when working application learning, we spend a lot of time doing retuning the features. So that's where deep learning comes. I'm not gonna get through theoretical background of deep learning because you probably have seen other talks. I just want to focus on one particular feature. Is the hierarchical feature representation of the data. So in that's what makes deep learning deep. The fact that you can take the same data input and you can just re-represent through different from a stack of hierarchical filters. And why is that important? Is because you can go from pixels, then you can start recognizing edges, and then from edges you can build object parts like a nose, an eye, components of your face, and then you can put it together, and then you get an object, which is the face. And that is structural representation. Take the raw data and start representing in terms of the structures rather than the raw representation itself. So in that particular picture, you can see that you start with with the raw image, and then you can remove the background. Why? It's because you managed to find out what is the structure and what is the background. And all of this happens through this signal propagation system. That's the major, the core idea behind neural networks. You first try to represent something, then you compute some error, which is your loss function, then you propagate back so that you can tune, that's the learning step. So we're gonna see now how those features can be used for anomaly detection with a particular configuration of deep neural networks, which is called Auto-Encoders. Auto-Encoders are, you can see, how many of you are already familiar with Auto-Encoders? Okay, quite a few. So Auto-Encoders is just, imagine to take a neural networks, then duplicate it and flip it. So you got one network, and then you have the counterpart, which is exactly the same network but flipped. So why you do that? So essentially, you take one input, goes through those hierarchical filters until you get to the middle point, which in a normal neural network that would be the output layer. But for an autoencoder layer of another network, which is just symmetric. And then what this second network tries to do is to reconstruct the original image. So at the end of the day, you obtain an identity function. So get X out. So you might think, why do I need this? To get the same input, you pass something for a filter and you get exactly the same input back. Well, because of the way we build that topology, you see that the number of layers are decreasing in size. So they always get smaller and smaller until you get to the middle, which is called the code. That code is something that contains the most amount of information of the original data. And when you reconstruct the original data back, you only do it from the code. That means you're forcing the algorithm to learn only what matters, only what is important in order to reconstruct the original data. And whatever is not important to reconstruct it, it just gets ignored. So how do you use Auto-Encoder for anomaly detection then? That's the algorithm. So whenever you try to do novelty detection, what you do is first you need to identify a training data set, which you consider to be normal. Normal means that it does not contain anomalies, or if it does, it's a very small percentage of the training set. So imagine you got your, you got a bunch of sheets, and then you say, all the sheets all look okay, I like them. So this is going to be my training set. And then use the autoencoder to be able to reconstruct any single sheet in this, this block. And then once you've learned what normal means you also learn how to re-represent the sheet through a compression field. And you can use that one, for example, you get one white sheet, and then you just get the same sheet back. But if you try to reconstruct a black sheet, what you get back is a white sheet. Because the training set only observed white sheets. So if you now try to reconstruct a black one, the model is not able to do so. So the model will always reconstruct something that looks similar to what is seen in the training set. And the reconstruction error that you get from the original data and what you get as output of the autoencoder is an indicator, is a score of how much this point is likely to be anomalous. Everything's clear? Yeah? So another use case of autoencoders, they're very powerful, is features compression. In that example, what we can do is that we can take the middle, the code, and we can say, you know what? My original data is 8 nodes, so the dimensional of my data is 8. And I would like to represent every single point in just three dimensions. This is something similar to PCA, but PCA is just a linear transformation, while in autoencoder you can have no linear transformation. It's much more powerful. And in that particular example, you see that if you, with a particular configuration of weights that you might learn through the training step, then each single input, which is one combination out of the 8 numbers, you get out, each input is a binary input, and then you get all the combinations. And if you pick one, it's gonna get represented with the numbers, with those numerical numbers like 0.89, 0.04, 0.08, and only those 3 numbers are actually able to reconstruct back what was the original input, exactly, with 0 error. That is very powerful, and essentially is something that you can use in order to reduce the dimensionality of your data set by preserving the most information possible. And after you do so, then you can actually apply some shallow machine learning. So you can still do anomaly detection or classification or whatever machine learning algorithm, but first you need to pre-process your data with autoencoders. In the examples that I'm going to show you, I've used H2O. So if you're not familiar with H2O, it's a platform for doing machine learning, and is pretty much production oriented. So it allows you to do prototyping, but then the nice thing is that you can move from a dev environment to a production environment with almost very little cost. And we're gonna see, so I have 2 examples that I prepared. It's actually come from the book, but we don't have time, I think, to do both of them. People are hungry, so we'll go with one. I chose the ECG, the electrocardiogram pulse detection use case because it's a combination of both feature compression and novelty detection. So let's see. Yeah. So I'll skip a few details. I will just focus on the concept. So let me zoom. Okay. So first thing you do is you import H2O like a library, like a module, and then when you do init, you start an H2O cluster on your machine. So unless you have some cluster already set up, if you do just .init, it's gonna start the local environment in your laptop. Then you can start working with it. So H2O already made public a dataset for the electrocardiogram. So we're just gonna use the same one. If you do .shape, we get the size of the matrix. It's a very small dataset just for proof of concept. It's around 23, not around, it is 23 rows and 210 columns. And what those columns represent is a particular sample in time of a piece of signal on an electrocardiogram that we're going to visualize. So if we visualize the data, that's how it looks like. You got a bunch of signals, okay? And you can see that most of the signals are pretty much on the same shape. They follow the same shape. There's an offset, so they are delayed from each other. But more or less they follow the same structure, is it? So, but there are the last three, which is the 21, 22, and 23, which correspond to those signals over here. So it's clear that those three signals are anomalous. So the goal is to train an autoencoder and automatically find out that those three signals over there, they don't follow the normal pattern. How do we do that? And it's just a bunch of utils for plots. That's how you build a model, an autoencoder in H2O. All you have to do is do an import, set a seed, because there's a race condition in training the deep learning network is done in a multi-threading. So because of race conditions, you may get different results based on the seed. And the seed is because of the hog wild is an algorithm for doing multi-threading learning of deep neural networks. Anyway, this is just an implementation detail. What you do is to create this class, and you need to specify a few parameters. Can you read that? Shall I zoom? Better? Okay. So you need to specify what activation function you want to use, and this is a hyperbolic tangent function. So it looks like a sigmoid function, but it goes from so the domain of the function is actually between -infinity and whatever real number, and then the output is between -1 and 1. So it's just an activation function like a sigmoid or rectified layer unit. The hidden is an array that specifies the size of each layer in your network, and it's very important that we keep it symmetric. Not going to tell you why this talk, because it's too much details, but it's important. It has to be the same size. So you go from 210, you go down to 50, and then those 50 nodes feed the next layer of 20, and then in the middle you get 2, and then from 2 you are able to reconstruct back the original signal. That means you can represent any single signal with only 2 numbers. It's amazing, isn't it? So let's see how that works. You do the train, okay, and then I've done some plot utils. It's going to show me each single point, each single signal on a 2-dimensional space. Look at that. So each point is one signal, okay, and they all bars on these 2 axes. And then the color is represent the reconstruction error. So if red means 0, 0 means no anomaly. It just has been reconstructed perfectly. If that color is higher than 0, means there was something wrong in the reconstruction. And we can see that those three signals, which is 20, 21, and 22, they got a higher reconstruction error. Let's try to visualize it in a more clear way. So, if you remember the previous picture, there were a few signals, and then there were three of them just, going on their pattern. They were not following the rest of the signals. This is the reconstructed version. So you get some weird signal, you try to reconstruct through an autoencoder which is being trained on normal signals. And what happens is that all of them look the same, because this is the normalization. And that means that that is the shape of the signal if it was an anomaly. If that was normal, that would be the signal. But because it's not normal, but it's an anomaly, you're going to see a very high reconstruction error because that doesn't look like the one we've seen before. So if we just try to plot all the reconstruction errors, we can see that the first 20 got almost 0, and then the last 3 got very high score. And if you put a cutoff point here, essentially you've done an anomaly detection. Now, that is the novel detection approach. And I want to show you how we can do something a little bit more advanced, very quickly. Do you remember when we visualized each single signal on two-dimensional spaces? I can do the same again using different seed. If I use different seed, I'm going to get another two-dimensional representation. So we defined a few seeds, and then I did the training many times. So at the end, what happens is that is yet another representation of the same data, but they just get collocated differently. This is just one of the many two-dimensional representations. They all contain the same amount of information. And then if I change seed again, I get this. And then I do it again, and I get this. Then I do it again. So every single time I change a seed, what happens? I get the point get redistributed. But have you noticed that those two guys here, they always end up very close to each other? So look at this. 21 and 22, very close to each other. 21 and 22, very close to each other. 21 and 22, okay, that little bit, but they're not too far from each other. And again here, you see? So that is a very important property. It's, you do it unsupervised learning. You're not feeding your data, you don't have labels. You're just saying that your data contains some anomalies. And this algorithm is able to first detect what is an anomaly, and secondly, classify, group together similar anomalies. So you will get that 21 and 22, they represent one type of anomaly, while 20 is an anomaly, but it's a different type. And all of these get for free. You don't need to label your dataset. And that is, in my opinion, the real power of deep neural networks. So you see, again, that are all good representation of the same dataset. And with that, you can apply a lot of other algorithm on top of it. So you can either use Auto-Encoder as the anomaly model, or you can use the Auto-Encoder as a pre-processing step. And then you can do whatever you want. Because now you represent your data in a much smaller dimensional space, so you can do clustering now, for example. Let's switch back to the presentation. If you're interested, you're going to find this on GitHub, so it's public. You're also going to find another example, similar one using digit anomaly recognition. But because it's late and we're all hungry, let's summarize. So what we've seen in this talk was, firstly, we listed a few real-world applications of how you can use anomaly detection. Then we cover a few techniques that you find in the literatures with their limitations. And then we propose this deep neural network system that actually need to solve, to remove those limitations. And In particular, we propose those two semi-supervised approaches, one based on novelty detection, the other one based on feature compression. If you are really interested in this topic, in this research area, there's a lot going on. If you really want to go deeper, you will find in this book that's been published, you're going to find a lot of stuff about advanced modeling like denoising autoencoders, contracting autoencoders, sparse autoencoders, variational autoencoders, stacked autoencoders. Those are all different variants of the basic idea of the autoencoder, but they give you much higher performance. And also, if you're interested on how to build a production-ready anomaly detection system, you have to be careful on because it's different from standard classification problems. So there are a few techniques that are really particular just for the anomaly detection, and all this is covered in the book. And I managed to get this 30% discount for anyone who's interested from the community. So you'll find this on the website as well. Thank you very much. Questions?
I think I have another question. But I was wondering if you could tell us a bit more. Okay.
Yes, what if you could tell us a bit more about the stacked autoencoders? I haven't heard about that before.
So stacked autoencoders means that, for example, it's used for initialization purposes. So stacked autoencoder means that you build one autoencoder. Let's have a picture here. Yeah, like this. You build this autoencoder, okay? And then after you've trained, you only take this output, and then from this point on, you start building another autoencoder. And then it's a recursive way of training autoencoders. That means that the first one is going to give you this set of weights. Now, when you train on a neural network, what you're doing is just finding the best metrics of weights. So you first find the weights here, then you take all the output of the first layer, and that becomes the input layer of another autoencoders. Then you train it, and then you go to the first layer of this second autoencoders, and the first layer of the second autoencoders becomes the input layer of the third one, and so on. So you can, instead of having just one topology like 4, 3, 2, you can have 4, 3, 2 for the first layer, and then you can build another one which is, I don't know, 3. Okay, here you don't have so much space because it's only 3, but let's suppose it was 30, 30, 20. Then you would take the output after training here, which is 30 nodes, and then you might go through another network which is 15, 10. Okay? And then you train it, and then you take the output at 15, and that might go into a different network, and so on. And by doing so, you essentially decrease the probability of overfitting. So it becomes much more robust. Yeah.
Great, thanks.
So it's hard to explain without seeing it.
No, I've got it. I've got it.
Yeah.
It's a training regime, right? It's a better way to minimize for exactly what you're looking for right there. Yes?
Yeah.
Which generally neural networks aren't aiming at what you're aiming for unless you do what you're talking about there.
So what I think in the previous talk, she said something very important, that one of the major problems with neural networks is that they tend to overfit a lot. So they, especially if the training set contains biases. So from an engineering point of view, if you really want to use those algorithms in production, you have to be very careful on regularization. But regularization is not like last or ridge regression. It's not that easy. It's something a little bit more complicated. For example, for that particular type of networks, you could use the stacked autoencoders, or you can use the denoising autoencoders. There are a bunch of techniques, and if you don't do so, I strongly don't recommend to use those in production.
Yeah, I can just shout. I was wondering, So I was wondering, you were explaining that you were giving an example of essentially a time series. So there is repeating signal, a particular shape in time in this heartbeat signal, right? So for this, I would assume one can also use recurrent neural networks.
Yes.
Is it possible to actually combine the recurrent neural network with auto-encoders, or is it too complicated?
That's a very good question. And actually, when you do time series anomaly detection, recurrent neural networks are more suitable, generally. So the way that would work is that generally, when you're working with time series anomaly detection, you build a regression system like a forecast model. So you're trying to predict what's going to be next. Then you compare. So then you compare what you measure today with what has been predicted, and then based on the difference between what the model predicted on today and what I can measure today, you do the anomaly detection, which is the same concept. You look at the reconstruction error. In that case, you look at the absolute error between what you predicted and what you measure. But it's conceptually they do different things. Because the LSTM is a stateful network, okay? So you need to feed the data in a certain order, and if you don't have a long history, it won't work, right? I mean, you need to train with long histories because the model needs to be able to memorize things and reuse it in the future. While autoencoders, they delegate the temporal sequence. So you encapsulate the temporal order in the vector representation. So in that case, we fixed on 220 samples. So our window is, okay, give me the last 220 measurements, and then based just on this window, I'm going to tell you if that window is anomalous or not. With LSTM, you have an theoretically unbounded history, past. You can take the whole history of your dataset between the first point in the signal up to, I don't know, years of the history, and then it will always tell you what's going to be next. Both of them are very powerful techniques. Yeah.
You said that you started with 50 nodes in the first layer, and you ended up in the middle with just 2 nodes, right?
Yes, so the network
looks
like this.
You managed to reduce the information just to 2 numbers.
Yeah.
But is there a parallelism with maybe the Fourier transformation of the signals, so that you can interpret your signal as having 2 frequencies? You can represent every signal with just the amplitude of those 2 frequencies, and maybe you can classify the signals based on the Fourier transformation of time.
So what you're saying is that I have a signal. I know there are 2 major frequencies. So I'm just going to represent each signal with the value of those 2 frequencies. So you're doing feature learning here. So you're putting your domain knowledge, and then you trying to do smart representation of the data, and then you apply anomaly detection, which works. Okay, you can do Fourier transformation, then inverse Fourier transformation, then you can apply the same logic. So yes, you can do that, but that assumes that you know what the data looks like because you know what the frequencies are, and you're doing some handcrafting of the features. Autoencoders, they figure it out. We need to worry about it. So if your signals really could be represented with just 2 frequencies, the model will figure it out. And that's the real power of neural networks. I mean, theoretically, it should figure it out. Then in practice, that happens only in 5% of cases, then the other 95 will need to stay there, some hand tuning of the network. But yeah, if you manage to do the right modeling, then it will happen.
How do you come to this architecture? Do you have a rule of thumb where to start?
Yeah. Right, so this is another preview. I wrote that in essentially when you build a production ready system, this is the outline. So that chapter essentially, now in that chapter here, I haven't covered, but I wrote down a list of rule of thumbs, which I don't have it now in the presentation, but essentially there are some rules. When you build an autoencoders, for example, if your data is numerical, you have to use a few activation functions. But if your data is a binary or is different nature, you should use different functions. And also the number of layers is actually does mean something, right? It's not random. You see that, okay? You having how many layers here? See, first layer is edges. Then from edges you can build parts of the face, and then composing parts of the face you get back the face. Okay, so adding more wouldn't have any benefit. If I would cut here, I will only get noses and eyes. Okay, so I wouldn't be able to reconstruct the face. So the number of layers is probably the easiest thing to guess, because it does have some intuition. Okay, how many nodes do you have here? This is where deep learning specialists get paid a lot of money. So they are very highly on demand, because those are the people that actually got some experience, so they got some gut feeling, and they can tell you, oh, I think here you should really use those real numbers. There's no, I don't think this is still an open issue. So you can do a brute force where you try to tune everything. You can do something a little bit more smarter. Remember back in time, there used to be the genetic algorithms for tuning your networks. Now that will be outdated. There are other techniques. Then this is the engineering approach. Just try out, see what works better. But if you start thinking, let's suppose this is your brain, and then how the brain would work, you might find some inspiration for defining why this should be 4 and this should be 3. We need to find inspiration from the nature. It's a really open question. But there are rule of thumbs. Okay. You'll find in the book. I can't tell you everything, otherwise I'm not going to sell it.
Okay, thank you. Thank you.
Oh, sorry, I gave you the microphone. Okay.
Is there a way to explore actually features that are recognized by the Auto-Encoder?
What do you mean by
different layers, like we have 50 neurons, and then 20 and then 2. Let's say also 4 and 2, but 4-dimensional space, it's kind of hard to explore features that are recognized to understand what really is doing. So how can we do that?
So generally, the way that works is that you create a matrix, a grid, where you have, layer 1, layer 2, layer 3, layer 4. Then you have all the neurons on each layer. Let's suppose that you have the same number of neurons, just for simplicity. So you have a matrix, okay? Then each single time you have one input feature, you're gonna color in black or white based on whether that neuron flags or not. Now, if it fires, you set the threshold, say, okay, if the activation value of that particular neuron is higher than that threshold, I'm gonna color it in white, otherwise I'm gonna color it in black. Or you can use some grayscale. And then by doing so, essentially, you get one input after training, get one input, and then you start visualizing this map. And then you can see that when, pictures of a woman, for example, every single time you feed the algorithm with pictures of women, you're going to see the same neurons fire, on the screen. And then if you start feeding with pictures of, cars, vehicles, you're going to see different areas of this map to start, widening. And that is exactly how the brain works, This is the activation places in the network that should, simulate the way that your brain activates the neurons. That's very cool way actually to do. So you take group of data and say, oh, let's see what are the neurons that get activated. And this is a very useful way for doing troubleshooting. If you see that your network is not behaving as you expected, that's something you want to try out. You start feeding with a bunch of data points that you know they are very similar to each other, and then you expect the same places, the same activations to happen. If that doesn't happen, means your network, it just learns some random structure. Okay, then you need to regularize. But if you see consistency in the activations, means that your network actually got smarter. So it's a good sign. Yeah. Okay.
Okay.
I mean,
So we often get faced with really, really imbalanced data sets, right? And I'm wondering if anomaly detection is really the way out in really imbalanced data sets. Like you make a case for fraud. Fraud is 1 in a million transactions, for example. So you have a lot of data about normal transactions, almost not about fraud. Is anomaly detection the way to go there?
so can you reformulate? So if you have a lot of data,
Yes, in the very imbalanced data sets, right? So you've got two categories, for example, fraud and non-fraud. Fraud is 99.99% not going to be there. It's only going to be there in tiny cases. Is this sort of anomaly detection the right way to go with really, really imbalanced data sets?
Yeah, so what I wrote down here is that if you're doing supervised learning, then you have the problem with the class imbalances. So if it's not balanced, then it doesn't work. Because you only learn how to represent one class, because the other class doesn't count, in your metric, training metric. So that approach doesn't look into the labels at all. I can't say it's unsupervised because it has the assumption that the training set contains only a small portion of anomalies, but the most of them are normal. So that's why I don't call it unsupervised, but it is unsupervised because that is not using any label. So yes, that's the only way to go in that case. And that's why supervised approaches fail in anomaly detection, exactly for this reason.
Thanks.
Yeah. Okay, I mean, we're gonna stay here tonight, so we can always talk later. I want to free everyone now, so we can go and eat some food. But before to do that, let's say thank you to our event sponsor, Think Big, that make this event happening, and also our organizing team, our organizer at that table. Let's give them a. There are about 10 people in the organization staff, and all the events that we organize is thanks to the whole crew. So thanks again, and enjoy the evening.